I think we should start. First of all, רויטל. בדיוק, זהו, אני... So it's a great pleasure for me to introduce Professor Yossi Mart from Haifa University, from the Rekanati Center for Marine Sciences, right? Yossi did his studies in Hebrew University first, and then in Texas A&M. Then he worked a few years in IOLR, in the Israeli Oceanographic and Lithological Center, and then here in Haifa University. And he works mostly in the Eastern Mediterranean and in the north of the Red Sea, right? So he will tell us about his work. As I say, often I ask Yossi's permission to do it. I strongly recommend to ask questions and to be involved during the talk. It makes things much more interesting to everybody, so by all means, don't hesitate to ask. And that's it. Let's start.
Yo, thank you very much. אתה קולט אותי? Thank you very much. I would like to talk about subduction. Subduction is my biased opinion, is that the most interesting process in earth sciences, and it is source not only of a huge amount of lithological variants, but also other things which I'll discuss in the talk. And the idea starts from the fact that we know the age of the seafloor, which its eldest the eldest age is here in the Eastern Mediterranean, as determined by Roy Granot of Ben Gurion University, and it's a Permian, 250, 280 million years, whereas the continents we know is 4,000, 4,500 million years. This means the age of the oceans is about 5% of the age of the continents. Why? Why? The ocean didn't exist before? Of course it did. But the seafloor is recirculating all the time. It's formed and swallowed again, and it formed and swallowed again, and the recycling occurs along subduction zones. So at present, we have subduction zone all around, mostly around the Pacific Ocean, which means the Pacific Ocean is getting smaller and smaller and smaller and smaller, until, if we wait long enough, Australia will collide with South America or whatever. There are other places of subduction in the Indian Ocean. In the Mediterranean, there is a stretch of subduction around Greece and Cyprus. There is a very interesting subduction in eastern Iran and Pakistan. And here in the Atlantic, there is some subduction here in the Caribbean. And with a big question mark, there is some people claim there is subduction here off the Mediterranean. Initiation of subduction is rare. Initiation of subduction is very rare. I marked three places here, and they are all controversial. One is here in the Yort fault or subduction zone. Chris Schultz from Lamont argued there is subduction on the western side of Hokkaido, that the Sea of Japan is subducting eastwards, and perhaps there is subduction of Algeria, the source of earthquakes in the Mediterranean, the western Mediterranean. So it's rare, which means we cannot look at the initiation of subduction. We have to invent it or envision it, anyone according to his idea. And the rocks that are formed, well, we know the Bowen reaction series that rocks start to form when they cool come from the mantle and come to the surface of the earth. We get ultramafic rocks, both plutonic and volcanic, with olivine and calcium-rich plagioclase, and we get also some pyroxene and plagioclase with the amount of sodium enriched gradually. And then the textbook showed that there will also we get the amphibole and the biotite and the quartz, but we don't. Because what we get at the mid-ocean ridge is basalt and some peridotites, that's all. This means that if we go to Iceland that sits on the mid-Atlantic ridge, we see basalt. You see the beautiful basalt here and the beautiful basalt on the other side, and you walk around the Anchor and you have volcanoes where they all produce basalts. Where are the other rocks? Where is the andesite? Where is the granite? Where is the rhyolite? Not there. They're not there. So what we get is during the subduction, there is gradual warming of the slab that goes down, and we get all type of rocks. For instance, volcanism that accompanies subduction is usually andesitic. Andesitic is Andes, named after the Andes Mountains, which is an intermediate type of magmatic rock. But why should it go down? Why should it go down? Everything floats on the asthenosphere, and why should the lithosphere penetrate into the asthenosphere? Some people said there is an inverse buoyancy. Inverse buoyancy is something that floats become denser than the material below, and then the lithosphere would dive down. But this is absurd, because what happened in inverse buoyancy, like the mid-ocean ridge, is that the lighter material, which should be lighter than the overhead, comes up. So to put negative buoyancy with this part of the subducting plate is strange, to say the least. And what we get in subduction, we get melt of the crust, or if you will, the brittle lithosphere. The composition changes because there is addition of water and also CO2 and nitrogen. And we get intermediate rocks erupting in the andesite form. And also, since we introduce into the upper mantle a block which is 2,000 kilometers wide and about 100 kilometers thick, it pushes away the basalt, the material that was there before, and it will come up here in the back arc basin. In addition, part of the downgoing slab comes up again. It goes down and it's detached and comes up again. Again, the idea is that this is a subduction channel, and the material going up goes to the same channel that material goes down, and so here could be some friction, or I don't know what. What it brings to my mind is, everyone is over 18? Okay. What it brings to my mind is that subducted slab is not a baby. It shouldn't come out the way it came in. Chemically what we get is that olivine and pyroxene change with the heating and the rising pressure and temperature of the subduction. This means if we take the olivine and we have no shortage of H2O from the sea and CO2 from the atmosphere, we get a reaction of magnesium silicate with hydroxide, which we call serpentinite. The serpentinite is usually, it can be hard, it can be soft, but its density is around 2.5, 2.6 grams per cubic centimeters. And in addition to this reaction, we get inorganic methane. Now, if we get inorganic methane, we have a means, environment that will start organic chemistry. And this is very interesting. In addition, the pyroxene would also not only to serpentinite. There is another way with shortage of water that it will give us a mineral called garnet, a group of minerals called garnet. Here I mark them with iron and magnesium, but there is a whole range of metals that accompanies the garnet. And the garnet is dense. I'll show you in a minute. So let's take a look at this, the evolution of methane, and we see that if we take CO2 and add hydrogen, we get methane CH4. The temperature required for the process called the Sabatier reaction is about 300 and 400 degrees, and in subduction we have no problem reaching this temperature. We can also produce ammonia in the process called Haber process, because we have plenty of nitrogen in the atmosphere. 80% of the atmosphere is nitrogen, so we have no shortage of hydrogen. We put it at pressure of 200 atmospheres and temperature of 450 degrees, and we get ammonia. And again, the temperature and the pressure are no problem in subduction. We have plenty of high pressure and high temperature. This means that life started in subduction. Therefore, I said this is the most important process in earth sciences. What it looks like. Here there is plenty of serpentine, which is greenish, yellowish minerals, while the garnet is a purple mineral. And as the process continues and pressure rise and temperature rise, the crystals of the garnet will grow larger and larger and larger, and the whole rock will become denser and denser and denser. It starts with being a basalt at density 2.9 gram per cubic centimeter, and it will reach densities of mostly garnet at 3.5, 3.6, 3.8, 4.5 gram per cubic centimeters, and it will sink into the stenosphere and go down. So this change of mineralization gives us the engine that drives subduction. Minerals change with reaction of water. I'll come back to the water issue later. Being from here, where no subduction takes place, my interest in subduction arose with my interest of Eratosthenes seamount and Cyprus and the interaction between the two. Yes, please.
Just to clarify, you say that this mineralization process is a driving force for the subduction? Do I understand?
The interrelation between?
No, the mineralization. What is the role? I didn't understand what is the role of the mineralization in the subduction?
The mineralization from olivine, mostly from plagioclase to garnet, will increase the density of the downgoing slab from 2.7, 2.8, 2.9 to 3.5, even 4 gram per cubic centimeter. This is the driving force of the subduction, because then it will sink down, it becomes heavier. And if you happen to pass in the offices and the downstairs of the Oceanic, of the Recanati Center, there is a beautiful piece of serpentine with large, huge crystal of garnet, about 3-4 centimeters large, and you can see it growing. It doesn't grow in the display, but it's beautiful, beautiful. So this is the Eastern Mediterranean. There were three legs of the scientific ocean drilling. There's a leg. There was a leg 13 in 1970, drilled one hole, 129 in here on the Nile fan. Leg 42, drilled 2 holes in marine rise that occurs here west of Cyprus. It's called Florence Rise, after a French small research vessel called Florence. And 4 boreholes were drilled in leg 160, 3 on Eratosthenes seamount, and 1 on the side of Cyprus. Eratosthenes, as you know, was the first person to measure the circumference of the Earth, and you look at the Wikipedia to find out. The idea of things that comes up from the depth of the Earth and come to surface were commonly attributed to compression. Plates move one against the other, and it's like the effect is like stepping on a tube of toothpaste. You press and something comes out with force. And this is a profile, imaginary profile. This is south, this is north. Here is Cyprus, and here is the Taurus mountain in Anatolia. Here is the Florence Rise further to the west. And you see the compression comes from this part, goes over this part. The Eastern Mediterranean is subducted under Cyprus. And indeed, what we see in Cyprus is lots of basalt that's called pillow lavas, pillow basalt. You see the type of the pillows, and this is typical to marine eruptions. Marine eruption would produce the water, the cold water, and the hot lava react and form series of pillow-like structure. This is a coin that's about an inch in diameter, so you can get the dimension. It's something like this, like a pillow. And it's of basalt, and it cools from the outside inwards. And the thing is that in Cyprus, also on the same mountain range, on the Troodos, you get a mixture of type of a serpentine of asbestos with peridotites. Here's the peridotite, here's another peridotite. Here another piece I noticed later, but I didn't mark it. And it used to be a mine of asbestos. People cut this rock and exported it for profit to mix with cement to produce building material. Then it turned out that people found out it is cancerous and stopped using the asbestos, so the mine is neglected. The fences are off, and you can walk around and take a look at the crest of the Troodos mountain. So I took these pictures, and you see that the asbestos or the serpentinite cover and embrace the pieces of the peridotite. The peridotite is heavy. Its density is around 3.2, 3.4 grams per cubic centimeters, but the asbestos and the serpentinite is 2.5, 2.6. So the mass of serpentinite coming up will embed the peridotite and bring it to the surface. So this is a mixture. We see this was considered to be the three rock types that I've shown. The pillow basalt, the serpentinite, and the peridotite were considered to be classical ocean floor, because this type of rock, what we find at the ocean floor in samples, mostly basalt, but also in some places, and I'll talk about it, the peridotite and the serpentinite. What we did with the ocean drilling program was to drill the Eratosthenes seamount, and this is the northern slope of the Eratosthenes seamount. And we see that indeed the edge of the seamount is driven down from depth of about 700 meters, 1,000 meters here, to 2.5 kilometers. It's pushed down towards Cyprus. So the seafloor is going down towards Cyprus. The thing is that we see here and we found is, whereas near the top of the mountain we found a considerable layer of Miocene rocks, here at the deepest and less erodible part of the section, the Miocene wasn't here, and we drilled directly to the Senonian. So when the motion of the Mediterranean Eastern Mediterranean started to subduct under Cyprus, this was the crest of the mountain. That's where most of the erosion was, and not this. Now it's deeper. This means that this was up and it was going down under Cyprus, and wonderful, we had an idea how the whole thing works, and the downgoing slab is acting like a wrench, like a crowbar where you want to open things. You put a piece of steel and you press it down, the other side comes up. We put Eratosthenes seamount down, and the Troodos jumps up like a cork of champagne. We wrote a paper about it. We gave some lectures. It was very well received, so we wrote some more papers about it. Here is a map of Cyprus, and you see the pink. This is the Troodos mountain with the basalt, the peridotite, and the asbestos and the serpentinite. Typical oceanic crust. Then we looked at the earthquakes. Now the color code is red is compressional, blue is extensional, and green is strike slip. And you see that the compression is not so frequent. Especially here we expect the Eastern Mediterranean to go under Cyprus. It doesn't go under Cyprus that effectively. Whereas the extension is very frequent, and also the strike slip. Now the strike slips, we know that is common because a year after we published our papers at the end of the cruise, the group from MIT published their results of GPS measurement in Anatolia and showed that Anatolia is driving very fast to the west. So all the greens that we see here is due to the westward travel of Anatolia. And we thought that we weren't very lucky, because if we were lucky, we wouldn't have published all these papers. So we went to model the subduction, since we cannot observe it. And we were invited, thanks to the hospitality of Professor Chris Talbot from Uppsala University. And we were invited to try to produce subduction. Now Chris was very polite and very British, and I told him what I want to do. And he listened carefully, and then he said, I don't think you'll get anything out of it, but if you want to waste your time and money, come and waste it. You're most welcome. So I came to waste my time and money. And in Uppsala, they have a centrifuge, a large centrifuge. You see, it's 2 meters, 2 meters across. It rotates. Now it rotates about a maximum of about 1,000 revolution per minute. When it was built, it would run up to 6,000. The point is that we increase gravity. We increase gravity, and we see processes that could go on surface. We can increase in gravity about 1,000 times, in 3 orders of magnitude. At about 1,000 revolution per minute, we get gravity increase of the g acceleration. Gravity acceleration is multiplied also 1,000 times, 3 orders of magnitude faster. And the experiment we built, scaled down with materials that they selected there in the laboratory before I came there, and put the material in a box, which is 8 centimeters in this dimension and 16 centimeters in this direction, also 8 centimeters to depth. And you put it in the sending on the side in the centrifuge, and it turns around, and things happen fast. On purpose, we could have introduced lateral push. We decided we're not going to use lateral push from all sorts of geological theoretical considerations. No lateral push. And this is how it starts. We have reduced size oceanic crust and continental crust, and it all flows on the asthenosphere, and it looks in a section. It looks like this. This is the continental crust. This is the oceanic crust. We put the asthenosphere in 2 stages. We put the first layer and we flattened it, and we put some dust of coal, a layer of dust of coal, and we put the second layer to envision motion in the upper asthenosphere. And you can see that after the experiment, there's not much of an ocean, of a motion here. There's some deformation, but not much. But what you can see that the continent is overlapping the marine slab, and the marine slab goes under the continent. Now, if in real life this thickness of the lithosphere would be about 120 kilometers, the top of the downgoing slab would be at depth of about 50-60 kilometers. At 50-60 kilometers, the formation of garnets forming a rock called eclogite, and the process is called eclogitization, takes place, and the density of the edge of the downgoing slab increases gradually. And this is the engine that pulls the whole thing down. That's what we suggest. And here you see the subduction starts, no lateral pull or push. Nothing. Only density. So we said, if that's the case, let's go to a more sophisticated model, and that's what we chose. We have here an image of the asthenosphere. The eta represents the viscosity that we used. This is 10 to the power of 3 megapascal per second. This is the power of 3, 4, and 5, and this follows more or less what is accepted for the densities of the asthenosphere, of the ductile continent and ductile ocean. And we didn't invent it. We found it in the literature. But in nature, this is 10 to the power of 19, and this is 18, and this is 17, something like this. Yivakasha.
This is the initial condition of the model? This is how it looked like before?
Yes, and the sizes also.
So why did you choose this geometry?
In a minute I'll discuss it. And then we had ductile oceanic and brittle oceanic, ductile continent, and brittle continent. We used the painter's putty. For this we used plasticine, and for this we used quartz wax, polishing wax. And they played with the densities with powder of barium sulfate with density of 4.5, and by adding the dust of barium sulfate gradually and checking the density, we reach the differences. So this is the running of the model with 5 layers, 5 units. And since we knew that friction plays a major role in the process, we put a drop of Vaseline here marked by the blue line on the side of the experiment, the rest being uniform. We put it into the instrument, ran it for 7 minutes, here, put it 420 seconds, and first we got subduction in this part, beautiful subduction. I'll show you in a section in a minute. Second, we got series of normal fault which indicate extension, and even some rift. There was a small rift here, and when we look at the section, so this is again the same figure that I showed before, but without the interpretation. You see one rift here and another rift here. This is extended, this is a bit pressed, and this is line B at the top. This line B, this is the section. The yellow line is the line where the two slabs were juxtaposed before the experiment started. And not you. What we see is that the continent collapses on the ocean squeezed under the continent and a bit uplifted, so it collapses seawards. The subducting marine trench indicating subduction that we know from the Pacific or even from the Hellenic trenches is moving seawards, is migrating seawards because of the subduction, because the continent advances seawards. Whereas when there's no friction, or there is strong friction, there is a collision and slabs are pressed once against the other. This means the amount of available water in the downgoing slab and the amount of serpentinite and its derivative that the water produce determine the type of deformation you get in the subduction zone. And if you go look at the chart of the Pacific Ocean and you see all the island arcs, arcuate island arcs, it all derives from the amount of water that is subduction and the serpentinite and its derivative that is produced. And here is a picture of a small rift that developed, extensional rift that developed on top of the overriding slab, where I don't know about you, as Brewer students, we told that it's all compression, because the continents move one against the other and collide. Then there was an experiment that was part of Liran Goren's master's thesis, and she had more patience than I did, and she took the experiment and ran it for an hour. And what happened is that we tore away a piece of the continent and produced an island arc, and here we have a back arc basin. If you wish, this is China, this is the Sea of Japan, and this is Japan, this is the Oceanic, the Pacific Ocean. Can you see it? Continent, back arc basin, islands, and ocean.
This is driven just by changes in buoyancy.
It was by gravity. Only gravity plays. Only gravity and lubrication.
So the lateral motion starts because of the
Yes, because this is denser than this. And I showed the numbers before. I don't remember them often, but I showed the number for not. You need difference of about 0.2, 0.3 grams per cubic centimeters to produce the motion. That's all. An experiment, and the order of magnitude of the experiment is an order of magnitude of real rocks. Unlike the viscosity, the densities are real. So the lines, again, the contact. And what you see here, those who have difficulty seeing, this part of the figure is the top of the experimental box, and this is the section. So this is oblique view, where you see the blue line, that's a section, and the yellow line is a surface. You look something like this. I'm looking at the table, I see the top, but I also see the legs of the table. The scale is in centimeters. Amazing results. Again, the picture of the serpentinite and the garnet, and I cannot emphasize it more. The development of the garnet at the expense of the serpentinite will enable the subduction and the sinking of the slab into the mantle, and the amount of serpentinite will determine the smoothness of the process, the friction that developed in the process. And we know that the friction, because the earthquakes that we see, the strong earthquakes that we see, produced in subduction zone. The 9.2 earthquake that ruined the atomic reactor in Japan 3 years ago, on subduction plane. Here is another picture of the garnet, and I want to give some details about the minerals involved in subduction. The pyrope and the almandine are two types of garnets, and you see that the pyrope has magnesium aluminum silicate, and the almandine is iron aluminum silicate, and there's a whole range of metals that come into the garnet group, and they're all silicates. If you will, even the zircon belongs to this family. So the hardness is 6.5 to 7.5 in Mohs scale, and the density is 3.2 to 4.4 grams per cubic centimeters. Olivines resembles the pyrope in its density and in the composition. It's iron and magnesium silicate, and you know that there's several minerals that are olivine group. The density is the density again is 3.2 to 4.5. The anotite, which is the end member of the plagioclase series, calcium rich. You have calcium aluminum silicate. The density is 2.6. That's all. So if we have peridotite, which is a composition of olivine and pyroxene and anotite, the anotite makes it lighter so that it remains on top. And the serpentinite, which is 2.5, magnesium ferromite, also has a huge selection of elements that join it, or metals and all sorts of other things. But you see the hydroxyl unit at the end. This is the water. This is the water. And the garnet is a semi-precious stone, and it's very nice. Now, there are two models for understanding the heat flow at oceanic spreading centers. This is the famous McKenzie model. It was determined to be a pure shear when you tear the lithosphere apart, and you have, this is my addition, the green line here and here, which are normal faults that bound the central rift of the ocean. And inside you have the structure that we see here of multiple normal faults. The heat is coming from the center of the structure. But we have subduction. We have no reverse faulting at the contact of the ocean continent. How do we get the reverse? How do we change the normal to reverse faults? And here we model, and the credit goes to Einat Aharonov. Here we modeled the change. We say we have subduction of, we have lithosphere, oceanic and continental, floating on the asthenosphere. And the oceanic part is denser than the continental one, mostly because there is a layer in the continent, there is a layer of 10 to 15 kilometers of granite, which is light. So the contact plane, which was normal at this point, starts to rotate because the net drive is into the left in this yellow arrow that is can you hardly discern. Here you see it better. So the fault plate rotate. At this stage, no motion here. It all remained where it was, so there are no earthquakes that accompany the process. But at a certain stage, change will start to occur here, the serpentinization, eclogitization I talked about, and there is motion, the earthquake start. So this is the beginning of the process, a change from normal faults to reverse faults. And then we see that, look at what happened to the rocks. The rocks undergo in subduction metamorphic processes, which we see here, the blue schist and the green schist and the granulite, and at the higher temperature and higher depth, the deeper depth, you have the eclogite. So you can adjust yourself. Temperature range of the eclogite is from 400 to 800, and the depth is 30, 40, 50 kilometers. Here it's not complete, 50 kilometers it can be. So this is the measurement we find in subduction zones. Not only that, but the depth where we have material going down. We have extension and faults occurring in the overriding slab. So the normal faults are easy way for material to come from the bottom up because it's weak. The location of the foot of the fault will determine the composition of the rock that comes up, because here the temperature and pressure are low, and here they're intermediate, and here they're high, but the fault forms a funnel or chimney, if you wish, for material to come up. And it will come up And since it goes fast, it will keep the composition that we have here at 100 kilometers or at 80 kilometers or at 40 kilometers. So when you walk in Eilat, on the mountains in Eilat, and you see rocks, magmatic and metamorphic rocks change all the time, that's because we're walking above subduction zone, and each place had its source at different depth, which means different temperature and different pressure. The last thing I want to talk about is a phenomenon called oceanic core complexes. I know that I didn't talk about continental or metamorphic core complexes. I didn't have the time and the ophiolite that involved with it. I mentioned the ophiolite. But I want to talk about the oceanic core complexes. And the oceanic core complexes are marked here. This is, you can see from the location map, this is Central Atlantic. There are 5 occurrences where you have the lithology called oceanic core complexes. What the oceanic core complexes unique of is their lithologic composition. They're not built of basalt. They are built mostly of peridotite and serpentinite. Peridotite and serpentinite. And the idea that follows their occurrence is a model suggested by Brian Wernicke in the 80s, and it's called simple shear as opposed to the pure shear. It's a model suggested by McKenzie, where the source of the heat that breaks the ocean crust apart is not under the mid-ocean ridge, but to the side, and there is a huge fault that's called detachment fault that crosses the lithosphere and comes to the surface and build this structure. And the evidence are the peridotite found at the seafloor. So there is some circular reasoning here, but that's what the conventional wisdom. Therefore, I want to bring forward here some research we did on transform faults. Now, I don't want to go into all sorts of irrelevant arguments, but the Dead Sea Rift is not an oceanic transform fault. Some presume that it is a continental transform fault. Some presume that it's not transform fault at all, but it's definitely not an oceanic. Because what determines the oceanic is different thing. I'll show you in a minute. And what we show here, there's another analog experiment that was conducted in the University of Rennes in northwestern France. And what we have here is this. We have a box, a tank of about meter by meter, about 30 centimeters deep, and this is filled with industrial honey with density of about 1.4 gram per cubic centimeter. In this box we have another box which has one half fixed wall and another half mobile wall, which can be moved at low rate and low but precise rate, and we can produce all sort of deformation in the material here. And here we put a layer of putty, silicone putty, that floats on the honey because its density is 1.2, 1.3, and this is covered by a thin layer of sand. And the sand is light colored, but the very top is we scattered dark color sand, and then we put the line that should be 2 centimeters apart of a net. In some places you can see that I managed to produce straight line. Not many, but some. And then we start to push. And if we say that this is the weakness zone of the whole experimental system, this direction would be the normal direction to the weakness zone, and we used oblique extension. So when we used oblique extension of 30 degrees, at first stage, at figure A, we produce a series of segments of spreading, connected by small transform faults, here and here and here and here and here and here. And this was spreading. It was getting wider and wider, and you see the white sand from underneath. So at the beginning we had several transform faults. As extension continued, the small transformed were swallowed in the opening ridge, but the large ones remained, and the length remained stable. This means after all the deformation that we did, the distance between this part of this ridge and distance on this ridge did not change. It didn't change. It remained constant. It remained constant, and that was the concept that guided us to work on the oceanic core complexes, which are marked here in green. Again, what we have on one side, the spreading ridge. On the other side, we have an old, relatively old oceanic crust. The temperature here is very high. Here the temperature dropped because it's under the water. This means the density here is about 2.6. The density here is about 3.1. Enough density contrast to produce subduction. We have it here, here, and here, and here. And this distance doesn't change, because if I don't know if you can see it, the circle is too small, but we have earthquake solution along the ridge and the transform fault. Here we have motion. We don't have earthquakes along this extension of the transform fault, which are called fracture zone. There's some vertical motion along the transform fault, and it is a scar related to the real transform, but the fracture zone, there's no motion. Relatively no motion. All the motion in the transform fault section between this ridge and this ridge, or this ridge and this ridge, etc., etc. So that's what we see here. This is the situation here. And another point I wanted to make is the difference or the effect of water on melting temperatures. If we take dry basalt and try to melt it, it will start melting at room temperature at 1050 degrees, and as we increase pressure, we get this line over here. As far we can go with pressure chambers in experiments. But if we add water to the of the mixture, about 5% or between about 5% of water to the whole volume, the huge drop in the temperature, melting temperature of the basalt, the solidus is moving from 1,000 degrees to 700 degrees at a pressure of, this is about 25 kilometers, this is about 50. You have the depth in kilometers on the other side. So the water make the basalt melt again if it goes down. So what I want to suggest, and this more or less, it was fast, more or less covers this part of the talk, is we have fracture zone valley at the edge of the transform fault. So on one side, we have the fresh oceanic ridge, and on the other side we have old crust, as we have in here. One side we have fresh oceanic crust forming, and on the other side we have old crust. Now the old crust is denser, and it subsides, easily because there is an existing fault here, the transform fault. That's a weakness zone. It goes down, and the gradient here is huge. It's about 120 degrees per kilometers, because we presume that the lithosphere, asthenosphere under the ridge is at about 10 kilometers. If you want 12 kilometers. So the gradient is huge, and we get very high temperature with relatively small pressure. Therefore, we won't get eclogite here. We don't have enough pressure, even though we have enough temperature. But we shall produce, on one hand, peridotites from the basalt. On the other hand, with the availability of the water, we'll use serpentinite. So the mixture of serpentinite and peridotite will, from this depth, will take the whole mass to the surface, as we saw in Cyprus, whereas some of the material continues to go down. So there is a possibility in unique places to produce subduction, not only at ocean-continent boundary, but in ocean-ocean internal boundaries, where the density contrast between one side and the other side of the subduction zone would be 200, 300 kilograms per cubic meter. Thank you very much.